Welcome back to Episode 3 of the Extreme Reliability Show. Episode 2 opened a lot of eyes, and it also stirred up a lot of emotions, especially among engineers. Some said they finally saw language that matched what they experience in the trenches. Some disagreed. Some felt challenged. That's exactly why we're here, because 1119 didn't expose a single failure. It exposed a fabric-level drift, the kind that spreads through timing, scheduling, orchestration pressure, and the gaps between layers. Today, we go deeper, and I invited someone who represents the toughest audience to convince, our hardware veteran, XRAD.
Dennis, thanks for having me, but let me be straight. I listened to episode 1 and 2 several times, and I wasn't fully convinced. You talked about message viruses, causal drift, vector fields, but I live in the lab. I deal with physical failures, margins, timing, windows, signal integrity, real boards. And when failures don't reproduce, or only show up once in 5,000 runs, or collapse under a strange transient, that's where I work. So when you said RCA is not enough anymore, it honestly felt like you were skipping what people like me do.
I understand why you feel that way, and the truth is I've lived that pain too. Long before cloud, long before hyperscale, I worked at Intertech, building ATS systems for power supplies. Debugging power modules is nothing like debugging digital logic. It's magnetic behavior, parasitics, thermal drift, EMI shadows, and sometimes just breathing on a probe changes the waveform. Well, you know what? Failures didn't repeat, not because we weren't good enough, but because physics isn't polite. You could stress test for days, finally catch a glitch, and then realize that the root cause you're chasing was triggered by an entirely different pressure pattern. And when it involved safety, a recall could destroy a company. So yes, I understand the weight engineers carry. The world didn't outgrow you. The world outgrew the time window humans are given to debug. RCA still matters, but the environment around it evolved. Back then, ATS was our way of reaching into the system from the outside, but today's data center isn't a single board. It's clusters, schedulers, NUMA zones shifting under load, groups breathing under pressure, kubelets reconciling state faster than humans can track, kernel micro-reactions shaping the entire stability envelope. You're not losing your craft. Your craft is expanding into a system-level reality.
All right, okay, I hear you, but if the old RCA can't keep up and your real-time causality architecture is the replacement, what exactly does that mean? And what is embedding in real terms? Because right now, it still sounds like a metaphor.
Great. That's the right place to challenge. And honestly, half of our audience asked the same thing. So instead of me explaining it, I want the person who actually lives inside the system to answer. XENOS, come in, please.
Thank you, Dennis. And XRAD, thank you for being honest. Engineers rarely get a safe space to admit frustration, so let's build from that. Let me start here. Embedding is not replacing what you do. Embedding gives you the visibility you always deserved, but never had the time or tools to obtain. Think of how cloud systems behave today. A scheduler shifts a workload across NUMA nodes. Memory residency drifts. The kernel adjusts frequency governors. So groups tighten or loosen pressure. Netlink floods small signals across the control plane. SysFs exposes transitions that don't look wrong by themselves, but together form a pattern of stress. None of these signals scream failure, but together they whisper, intent and behavior are drifting apart. That's the birthplace of every major outage, including 1119.
So, you're not watching for what breaks. You're watching where the system is leaning before it breaks?
Exactly. You work at the point where a component gives up. I work at the field where the pressure that makes it give up is forming. Let me put it in more familiar terms. when a kernel starts reshaping interrupt affinities, when memory hot pages start migrating in odd patterns, when C group pressure oscillates more than the workload should require, when API intent doesn't match orchestration behavior, when scheduler fairness begins to jitter. These are not failures. They are pre-failure geometry. They show where causality is bending. That's where I live. Not outside the system, monitoring outcomes. Inside it, where the causal field forms. If you want a simple metaphor, I don't observe the system. I move my bed inside it. I live where the causality sleeps and wakes.
XRAD, this is why I said RCA isn't dead, it's just moving upstream. You're still essential, but instead of waiting for one deterministic failure, you're now seeing the entire field that shaped it. Debugging becomes faster, failures become predictable, and the system finally becomes governable. Our job isn't to replace engineers. Our job is to remove the unfair conditions engineers have been forced to work under.
Okay. I'll admit that actually makes sense. But there's still one thing I don't fully get. It's one thing to read all this, it's another thing to actually enter the system. How do you physically embed? How do you stay inside? Where's the entry point?
That's the right question. And the answer needs its own episode. Next time, we talk about the physical corridors, PCIe sideband behavior, power sequencing vectors, I3C and SM bus observational telemetry, JTAG traces, signal coherence paths across the fabric, and why I never read payload, only causality.
If episode 3 is about embedding before debugging, then episode 4 is about embedding inside the hardware reality. We're going to open the machine, show how X-Series gets in, how it stays in, and how it governs without touching user data. We'll see you in episode 4.